How come pilots have to know about electricity? I understand that a lot of people don't like electricity. It didn't sink in well the last time somebody tried to teach it to you, but it is very important, and there's three reasons why pilots need to know about electricity. One, because so many things are powered by electricity. Two, because so many things on the airplane are controlled by using electricity. And number three, because so many indications the pilot gets in the cockpit is done via the use of electricity. Here is your brain on electricity. Hopefully, by the end of the sections on electricity, that sound will have come from each and every one of you. There's a lot of different components that are found in electrical systems, and you're going to need to be able to recognize the symbol, be able to draw it. As a matter of fact, you need to know what the purpose is, why is it doing, what's it doing on the aircraft, why do we want it, and function, how does it work, what is it doing, how does it do its job. And why do you need to know this? Because you're going to be seeing so many electrical schematics on aircraft for the rest of your career from a 172 up, that you need to understand it so you can figure out how the system is operating. So, conductor, that one is really, really easy. Here is the electrical symbol for a conductor. Effectively, it's just a wire. What is the purpose? That is, why is it on board the aircraft? So we can transfer electrical power from one place to another. What's its function? How does it do its job? It does it by allowing electrons to flow very, very easily. It's got a low resistance. Aircraft wires are typically made out of copper or aluminum. On little airplanes, they're all copper wires. On bigger airplanes, some are going to be aluminum and some are going to be copper. They're going to use copper where the wires are going to get bent a lot, like going to the landing gear. Aluminum cracks a little bit easier if you keep bending it back and forth. So large aircraft are only going to use aluminum wires where the wire isn't going to get bent. Retentivity, since neither copper nor aluminum have any iron, cobalt, or nickel in them, they're going to have no retentivity. So if we turn off the electricity, electromagnet power or electromagnet lines of flux will go down to zero. Here's a picture of some copper wire. On airplanes, the copper wire, they tin plate the copper so it doesn't corrode so easily. So on airplanes, if you take the insulation back, you're going to see that tin plating. It looks like it's silver, but it's really tin plated copper. Here is some wire bundles. You can see a wire bundle going in here. You can see a wire bundle going in there. You don't have to write it down, but it's typically Teflon is the base material for the insulation on the wires. That's a couple of wire bundles. Here's a couple more wire bundles. As you can see, they're tied together so they stay nice and neat and don't touch anything. This is actually the back side of a circuit breaker. Busbar. Busbar is typically drawn in a rectangle, the electrical symbol for a busbar. And you notice these are the electrical symbols for electrical components. These are the symbols for electrical components, not what they actually look like. But this is typically the way they're going to be drawn on schematics. They'll usually draw on the busbar how many volts and whether it's AC or DC to identify it. Why is it on board the aircraft? Why do we have busbar? To make it easy so you can connect and disconnect a lot of components from the battery and or the alternator. And its function is connecting to the power source. We're going to get to it in another slide, but you can connect the battery to the busbar, and now you can connect stuff to the busbar. And if you open or close a switch between the positive side of the battery and the busbar, you can turn everything off on the busbar or turn everything on that's connected to the busbar simultaneously. And there's a picture of one kind of a busbar. You can see, it's hard to see there, it's kind of fuzzy, but those are all connections, screws that you can hook wires up to. Here is a busbar inside of an aircraft, and this is the back side of circuit breakers in here, and there is a copper strip connected to the circuit breaker. So when you flip on the master switch, the positive side of the battery is connected to this bus bar. So now everything hooked up to this copper strip is connected to the battery. And here's another example. These are all, again, these are circuit breakers in the back, and you can see a copper strip right here, and there's a copper strip right there, and those are all bus bars. Ground connection. Here's the symbol for ground. 3 wires, or 3 lines rather, getting smaller. I've seen some with 4, but usually it's 3. Why do we have ground wires on the airplane, on the helicopter? So we can save weight. We're literally going to use the fuselage and or the wing or of the aircraft that's already there to provide part of the electrical wiring of the system. If we have a battery, for instance, and we connect the negative side of the battery to the fuselage, we can run electrical power through the bus bar, and we'll say we put a switch right here, and we run a long wire out to the tail of the airplane to a light bulb. At the other end of the light bulb, we can have a 2-inch long wire and connect it to the fuselage, and now the fuselage is the wire that connects the negative side of the battery to the ground side of the light bulb, and we only have to have 1 wire. So this is extremely typical in aircraft and in cars and motorcycles for that matter, where we can save quite a bit of weight and complexity just by using the chassis in a car, or the fuselage or wing or airframe, if you will, of the aircraft for that return wire. And how does it do it? Its function is by connecting those components to the power source. In this case, it's going to be the negative side of the battery. Here is a picture of some wire coming down, and it's touching this piece of metal down here, and that's bolted down to this piece of metal, and this piece of metal looks like it's riveted onto the fuselage or whatever. Fuselage, okay. Making sure I spell fuselage right. So now you don't have to run a separate wire all the way back to the negative side of the battery. You can use the fuselage to do that. I think I got another picture. Sure enough, here it is. This is the engine case. This is actually the engine, and this big electrical connector right here, that's actually going to the fuselage and connecting to the fuselage, and of course that's connected to the battery. So all of these wires coming in are ground wires, and so they're all now grounded or touching each other. Everything connected to the ground is touching each other. So if you have that battery and the negative side of the battery is connected to ground, and you go way out to a light bulb, and the light bulb is connected to ground, and you have a motor, for instance, and it's connected to ground, everything that's got this ground symbol on it is connected to everything else that has the ground symbol. Of course, electrons go from the negative side of the battery to the positive side, so they're going to try to go in this direction. And of course, electrons are going to go from the negative side of the battery. They're going to go in this direction. So it works out all right. The electrons all leave the negative side of the battery, and they all come back to the positive side of the battery. Hey, there it is, battery. Battery. Small, long, small, long. There's the battery. And of course, the short line is the negative, and the long line is positive. If you have to draw a battery on the test, make sure you put the negative and the positive in there. Each one of these symbols of the short line and the long line are representing a cell. So, for instance, you could argue that this represents a 2-cell battery. So, if you technically in a flashlight with 2 D cells, really it's 2 cells together make a battery. You got to have more than 1 cell to make a battery. We just tend to call them batteries. What's the purpose? Why do we have batteries on the aircraft? To store electrical energy so we can use it for some purpose. Its function, how come it's on there, or how does it do its job? It changes chemical energy. We'll talk a little more about batteries in another section, but batteries store chemical energy, and it converts it to electrical energy when it discharges. Here's a couple of pictures of a battery. Here's an airplane battery. It's made by Gill. They got the thing about using pink plastic, and this battery has 6 cells in it. Although no matter how many cells, we're still going to draw that diagram or that symbol with just 2 cells in it, and we're not going to draw every single cell in it. If this has 6 cells times let's see, 1.2 That's going to give us 12.6. I think that's 1.2. It's going to give us 12.6 volts. So in an older 172 that runs off of a 12 or 14 volt system, they're going to have a 12 volt battery and it's going to have 6 cells. But in a newer aircraft where you need 24 volts instead of 6 cells, there's going to be 12 cells, and then you'll get 25.2 volts off of it. 1.2 doesn't sound right. Nope, it can't be right, because 6 times 1.2 would be like 6. Oh yeah, now I remember. It's 2.1. I got the 1 and the 2 reversed. So lead acid batteries, you don't have to know this right now. You don't have to write these numbers down. But if each cell, 2.1 plus 2.1, if we keep adding those up, we'd get 12.6. Or if there was 12 of those, we'd get 25.2. Well, I'm glad I remembered that lead acid batteries, each cell is 2.1. There's another picture of a different brand. This is Concord. They make airplane lead acid batteries. One of these is going to be positive, and one side is going to be negative. And that's enough on batteries. SPST stands for single pole, single throw. That's what the SPST stands for, single pole, single throw. The electrical symbol for single pole, single throw switch looks like this. It's typically drawn in the open position. You don't have to draw the word open next to yours when you draw it on the test. When I say draw an SPST switch, this is in the open position. That also means that the circuit is incomplete. That means no amps are flowing. And that could also be described as the switch being in the off position. Purpose: why is it on board the aircraft? So we can turn things on and off. How does it do it? By opening or closing the circuit here. Of course, that's the open position. You don't need to draw this, but this would be the closed position. And that would be, generally speaking, would be on, or you could call it a complete circuit. And yes, amps are flowing. And I'm sure I have a picture here. Here's one that switch on your house, in your home or your apartment. That switch is a single pole, single throw switch. You'll notice that the diagram, single pole, this thing right here, you could call this a pole. It's flopping around. There's only one pole, a single pole flopping around, and it can only throw electrons. It can only throw electrons into a single circuit. Hence the single pole, single throw description. And so that switch, typical light switches are single pole, single throw switches. Here's a couple of pictures of airplanes. Of course, airplane switches. Of course, there's on and there's off. Typically, they mount them so up is the on position, and it makes a connection between the two. Of course, inside of there's a pole flopping around, and you're grabbing that handle and moving it. Closes or opens that pole. And there are some single pole, single throw switches. This one is spring loaded. It's spring loaded and pushes it out. So when you push it in, it closes it. Essentially, it works like this. There's a spring holding it open, and when you push down, that makes the switch close. And then when you let go, it's spring loaded back to the up position. So it's still a single pole, single throw switch. It just happens to be spring loaded into the off position. Ammeter, this is a very, very difficult gauge to draw the electrical symbol. It's a circle with the letter A, capital letter A in it. Woohoo, that's really hard. Ammeter. Why are ammeters on board the aircraft? So it gives the pilot an indication of system condition. You notice that this is the exact same purpose as a hydraulic pressure gauge. The purpose is the same. Now how it does it, its function is different. Certainly an ammeter is different than a pressure gauge. It displays a quantity of electrons that travel past a place in a certain time. In fact, wow, except for the word display, this is effectively the definition of amps, or current flow, a quantity of electrons for a particular unit of time. I'm sure I got a picture here. Here's an ammeter that you might find in a single-engine Cessnas. I know this is a slightly different version, but they generally, it's plus on the right and it's negative on the left, and if the needle moves to the right side, that's good, because it means that the battery is charging. They set this ammeter up in the battery circuit So it tells you that the battery is charging, or of course if the needle is on the negative side, for instance you got in pre-flight the airplane, turn the master switch on, the needle is going to be slightly on the negative side, and that means the battery is discharging. In some other aircraft like Piper, or if you fly the Seminole, or a lot of twins, they're going to have an ammeter for each generator or alternator. Instead of telling you how much the battery is charging or discharging, the amps it's telling you, the amp that it's displaying is telling you what the generator is putting out. So in this case, the needle would move farther to the right whenever the generator or the alternator was producing more amps. Of course, it doesn't have, there's no negative on this, so it doesn't tell you specifically if the battery is discharging. We'll talk some more about that in another section. Variable resistor. The symbol for a variable resistor, make sure you have really nice sharp points here. Doesn't matter exactly how many of these you got, how many back and forth angles you've got, but you need to draw an arrow through it and fill in the head of the arrow. That's the electrical symbol for a variable resistor. You've operated variable resistors, for instance, a volume control on a radio. You turn the volume control to the right, and that reduces the resistance. The resistance goes down, but that allows more amps to flow, and that allows the volume to go up. So you've operated variable resistors before. So the purpose is to control circuit amperage, and of course more amperage is going to allow things to go faster. If it's a variable resistor to an electric motor, it'll spin faster. If it's to a light bulb, the light bulb will burn brighter. If it's to a speaker, the speaker will have a larger volume. How does it change the amperage? It does it by changing the resistance. So if we get rid of this junk over here, we could put a battery right here. Whoops, didn't need all that. Well, that's a ground symbol. And we could put a light bulb right here and run this to ground. Now the negative side of the battery, electrons are going to try to go from the negative side of the battery through the light bulb, through the variable resistor. If we turn the resistor typically clockwise, that reduces the resistance, and so more amps can go through the light bulb, and the light bulb is going to be brighter. If we turn the dimmer switch, in this case it's a variable resistor, we turn it to the left, then we have higher resistance or higher ohms, and so less amps go through, and the light bulb's not as bright. So we can change the amperage to do a lot of different things, and we do it by varying the resistance of the circuit. And I got a picture of a couple here. And here is a variable resistor. This arrow right here says turn it to the right, and it gets brighter. Here is the inside, what a variable resistor looks like, and this is just where the switch gets hooked on. This is the part that you would rotate left and right. This is the variable resistor itself. And here's an electrical schematic. So the electrons have to travel through this bar right here, and they can go in this direction. If we turn the volume, in this case, down, so this bar is right here, then the electrons are going to have to travel through more material to get to wherever they're going, so the resistance would go up. So this knob, this is showing the inside of the variable resistor, so we can change that resistance manually to make things get louder or go faster. And here's a picture of the inside of a variable resistor. Coil. The electrical schematic for coil has bumps on it, and we're looking for essentially perfect semicircles here. We'll see how perfect I can be. Watch out, a variable resistor, the bumps are really nice and sharp, and in this case they're nice and smooth, round bumps, and it's not a matter of how many. Get at least 3 or 4 of them in there, you'll be fine. Purpose: why do we have coils on board the aircraft? So we can control a correction. Yeah, why do we have coils? So we have a controllable electromagnet. Actually, you could actually cross out the word electro and say we could have a controllable magnet, because now we can vary how many amps go through it, because the more amps go through it, the greater the strength of this electromagnet. What's its function? How does it do its job? It's essentially an energy conversion device. It takes electrical energy and changes it into lines of flux. And of course, I already said strength is controlled by the number of amps going through it. The more amps, the more lines of flux, the stronger the electromagnet is. Less amps equals less lines of flux equals less strength. And here's a picture of a coil. You run electricity through it. One end of the coil ends up being the North Pole. One end of the coil ends up being the South Pole. And you can see the lines of flux coming out of one going into the other. So here's all the lines of flux there, typically on the outside of the coil. Unless you happen to stick a chunk of iron in it. For instance, if you stick a nice chunk of soft iron in it, it's much more permeable than air is. So these lines of flux will get sucked into the permeable core, and now they're all concentrated and they'll be all much closer together. So typically you see with a coil, and you don't need to write this down, but here's a coil. Although they may not write it into it, they may draw a couple of bars next to it, and those bars are talking about the permeable core, and that shrinks in. That doesn't shrink. It pulls in the lines of flux, so they're all really concentrated inside of this iron bar, and that makes this much stronger. We have a lot more density, if you will, a flux density, how many lines of flux there are per cubic volume, per cubic inch. And so it effectively makes the electromagnet stronger, even though we didn't have to use any extra electricity to do it. Motor. The electrical symbol for a motor is a circle with a capital letter M in it. Very difficult, just like the ammeter, difficult. Purpose. Why do you have motors? To supply a whole bunch of kinetic energy. How does it do it? What's its function? It's an energy conversion device. Wow, another energy conversion device. Imagine that. It takes the electrical energy that it's being supplied and it changes it into rotational energy or kinetic energy. And some are reversible. For instance, we'll talk about it later, but you can have a different kind of a switch, and you can have a flat motor, and you can make the flat motor go in one direction or the flat motor go in the other direction, and of course it's hooked up to the flap, and it makes the flap go up and down. So flat motors on 172s are reversible, and they even have reversible alternating current motors, like flat motors in a 727 run off of alternating current instead of direct current, but they're still reversible. And I have some pictures of some motors. Oh yeah, I forgot to tell you. It's a good thing I put the notes in here, that if you open up the inside of a DC motor and you open up the inside of a DC generator, you're going to see that it's got a whole bunch of wires and sometimes some permanent magnets, and they're effectively the same. That is, if you took a motor and spun it around, it would generate electrical power, or if you took a DC generator and gave it electricity, it would spin. So we're going to get to it in another chapter, but there is such thing as a DC starter motor, and after start, it acts as a generator. And that's the name that we're going to call that when we get to it. And here's a picture of a starter motor. Here's the starter motor on an aircraft engine, and it's bolted right smack into the engine. And here's that big positive wire. And of course the engine case, or the motor, it's grounded to the engine case, and the engine case is grounded to the airframe, and the airframe is grounded to the battery. So we only have to have this one big wire coming into the starter motor. Here's a picture of a starter motor. This is a solenoid or a relay. You don't have to write that down now, but this mechanism here actually pushes the starter teeth into the starter, and then the starter gets to spin around. That's pretty typical on a whole lot of cars and on some airplanes. Here's another starter motor. Got the wires coming in. Shaft on the is going to spin around. Yay, starter motors. And here's the inside. You don't have to draw this on the test, but you'll notice around right in here on the inside is a permanent magnet, and then there's tons and tons of wires, and of course those are going to be electromagnets, and the lines of flux repel against each other and attract, so that it converts the energy, electrical energy, into motion. Okay, basic DC circuit. If I give you this diagram on the test, you're going to need to be able to label it. So let's try a different color. So this run right here, this would be a ground. Let's see if I can do all of these. This part right here would be a bus bar, and bus can be spelled two different ways, B-U-S or B-U-S-S. Either one of them is correct. Here's an ammeter. This right here is a battery. and of course labeled plus and minus. Here is a single pull, single throw switch. This right here is a motor. Oh, almost forgot. Wow. Conductor. Oops. Fix that in here. And let's see, here's a coil. And of course, we have a variable resistor. Let's see if I got everything. Dun, dun, dun. You don't have to label all the grounds or all the conductors. So, what would happen here is that electrons leave the negative side of the battery and they're going to try to get to the positive side. So they're going to leave the battery and go through the airframe, and they're going to try to go places. Of course, if this switch is in the open position, no current can flow across it. The electrons aren't going to be able to jump this gap of air if the battery is at a low voltage, even if it's at 28 volts. So the motor's not going to spin. Now, if we close the circuit, turn the switch to the open position, now electrons can go through the motor. Of course, it'll use up some energy, and the electrons will go through the ammeter to the positive side of the battery. Essentially, you can think of the negative side of the battery as having too many electrons, and the positive side of the battery doesn't have enough. And so opposites attract. So these negative electrons are going to try to find a way to go to where there's not enough electrons. So if this one electron gets all the way around, this side doesn't have any more excess electrons, and this proton over here, where there wasn't enough electrons, where it was positively charged, now it's neutral again. So the battery's going to slowly be discharging, and of course if we have an ammeter in the battery circuit, then the needle is going to show slightly to the left. It's going to show a discharge, and that means the battery is draining, and at some point, at some length of time, depending on how many electrons are draining out of the battery is going to go dead. And of course here we have a coil, lines of flux emanating off of it. If electrons go through it, we'll have lines of flux. We can turn the variable resistor to clockwise typically, and that'll have less resistance, less ohms, so that will allow more amps to go through the electromagnet, and we'll have a stronger electromagnet. And of course the electrons will also end up going to the positive side of the battery, and this electron won't be there on the negative side, and it will have come around and gone to where there's not enough electrons. So after a while, electrons keep going, the battery's slowly going to drain, and at some point the battery will be dead. And of course, when no electrons are draining, the ammeter will come back up here to the center, to 0, and then nothing would work. So there is a basic electrical circuit. Literally, this is the basic kind of a circuit that you would find in a Cessna 172. Of course, you've got to have some master switch in here to connect the battery up to the bus bar, but as soon as you hook the battery, the positive side of the battery, up to the bus bar, now you can use all of your components. And of course, one way, if you look at this kind of a schematic, you could draw all these grounds and connect them together, because electrically they're all connected together. We're just going to use the fuselage or the empennage or the wings or some other metal part of the airplane to be the wire for us, be the conductor. But that wire doesn't have to be there since the metal of the airplane's there, so it's going to save weight.